Hi there. Colin's just getting suited up, so while he does that, thank you all for coming. Thanks for inviting us, Hans and Julia. It's really good to be here. We were going to do something actually. We were going to have 2 lightning generators, and we were going to try and sail 2 hot air balloons through the lightning generators with a cloud of smoke and a big luminescent ball. We're going to recreate a storm, but the health and safety executive decided it was too dangerous for you, the public. So we're not doing that. Instead, we're going to show you a fusion reactor.
That's okay though, because there's no particular licensing associated with fusion reactors.
Believe it or not, yeah.
Believe it or not, so they're allowing us to do that.
In fact, yeah, some of the bits from this you can get off eBay. In fact, we quite frequently get things off eBay. We recently got some hydrogen thyrotrons from eBay, which is the trigger unit for a nuclear weapon. And I think Colin managed to get 3, didn't you, quite cheap off the eBat. So today we're going to show you this. I'll tell you a little bit of the background about it. Basically, I wanted to make a star on Earth, which is not the easiest thing to do, as you can imagine. But I saw this thing called sonoluminescence, which is where you can get a spherical bell jar, a jar like a retort full of water, and you put a bubble in there, and you have a standing wave in there, and it collapses the bubble, and you get a tiny little point of light in there, which is in fact it's very, very hot. It's in the orders of tens of millions of degrees centigrade. It's a little ball. What is that awful noise? And stop that. And but it's very, very small. And it's very hard to see. So Colin, I told Colin that I wanted to do this, and
I said, well, we could do that, but it's going to be very hard to do, and you're going to end up with a very tiny speck that nobody's actually going to be able to see, which is all very interesting as an end in its own right. But frankly, as a piece of art, it's pretty poor. But I said, what I do know about is something called a fuser. And this was some technology developed during the early 50s as a way of achieving nuclear fusion, which is obviously everybody's goal in terms of limitless energy and the like. And the technology was developed by a chap who was involved with TV. And the idea was, instead of the traditional way of achieving, well, there are 2 main ways of achieving fusion, but both of them really focused on getting something very, very hot. And the problem with that is hot things, everything isn't at the same energy. There are some things that are a little bit hot, some things that are a lot hot, and some things that are very, very hot. And you get a distribution of particles. And to get things hot enough to actually smack together hydrogen nuclei and fuse, you have to be very, very hot, and things just diffuse out and go away. It's just very hard to do. And this chap developed an entirely alternative way of doing it. Which was to have 2 grids. So inside this bell jar, some of you in the distance might find this hard to see, so I'll just kind of describe it to you.
It's up there, Colin.
Perfect.
The doodah.
So on the outside, you might just see there's an outer grid of wires. So there's about a 12-inch diameter set of wires here on the outside, and then in the middle there's a much smaller grid of wires.
They're the same, though. Yeah.
Yeah, you'll see this much better once we actually turn it on. And what we do is take the pressure inside this down to about 1/millionth of an atmosphere, so there's very little gas inside it, and then we charge the inner grid to about minus 10,000 volts. And everybody's probably seen neon signs where you ionize the gas. Well, that's effectively what happens in here, but because the pressure is so low, instead of the particles banging about and just having random motion, they rush inwards towards the inner sphere. Now, you've started off with quite a large area of the outer sphere. The area of the inner sphere is a lot smaller. So as these things rush inwards, the pressure goes up hugely. And what you find out, by the time you get to the middle, you've got a ball of incredibly hot, effectively very, very hot plasma, which is around about 10 to 15 million degrees centigrade. And if the gas you choose to run this on is deuterium, 2 deuterium nuclei will fuse together, and you'll produce helium.
It's not really deuterium, no.
My beautiful assistant has some deuterium.
Not really.
However,
if we were to put deuterium in it and fuse it with deuterium, you'd all be bombarded with fast neutrons and you'd die in about a week, so we're not going to do that.
Yeah. So
health and safety.
We did consider that, but we thought we might get a few letters of complaint.
Yeah.
So instead what we're going to do is we'll demonstrate the same principles, but instead of using deuterium and killing all of us, we're going to use initially air, and then we're going to try a couple of different gases so you can see the different effect on the lights. So what we'll do is we'll turn this on.
It's interesting to note that the sun's 93 million miles away, right? And the surface temperature of the sun is around 10 million degrees. This little ball of plasma you're about to see is about 10 million degrees too. But it gives you an idea of how big the sun is when at 93 million miles over a vacuum, it can heat us up as much as it does. It's a ferocious furnace under whose kindness we exist. But this is obviously a lot smaller, but at the same temperature, and the vacuum stops the heat from getting out. So you won't notice any appreciable.
It hasn't affected us.
Change.
We're still quite normal.
Should we do it then? We need to bring the lights down if we can. Thanks. That's great.
So what's going to happen here is we're going to turn on the vacuum pump, and that's basically going to reduce the pressure in this setup to a lower and lower value. And then when it reaches a critical threshold, which we hope it will reach before the end of this presentation, when it reaches a critical threshold, we're going to turn on the high voltage. And that, as I said, will ionize the gases, and then we'll see all the particles rushing into the middle, and there'll be this little shock wave and ball of intense plasma in the middle. Like all good experiments, there's that little element of not knowing quite what's going to happen.
It might not work, in other words. It did come in. Oh, there we go.
Right.
There we are. Sure is pretty.
So
you can't really see, if you were closer to it there, you see the sphere there. I mean, it is in effect a tiny little star.
So what you can see here, you can actually see, now it's got the plasma inside it, you can actually see the two grids quite well. So you can see the outer grid of wires.
That's good.
And then the inner grid. And the difference between them is they're about 5-to-1 diameter-wise, 25-to-1 surface area, so we're getting a very significant compression. And the particles coming in are coming in with 10,000, across a 10,000 volt difference, which means they're really going with a lot of energy. And yeah, what we're seeing in the middle is a ball of superheated plasma, and if we put deuterium in there, we would achieve nuclear fusion. But as Paul says, that's not a very good artistic display.
The problem with fusion is containment, you see. You see that thing squirting out the side there? That's it's called a poiser. It's like it's basically where the containment field created by the inner grid is imperfect. It will try and get out basically because the pressure and the temperature, the environment in there is so intense and horrible. The other thing that happens is that because there's kind of a solar wind coming off it all the time, because of the intense temperature in there, the inner grid is made of tantalum, which is a very, very hard and very tough metal.
High temperature, high melting point.
And a very high melting point, but actually it's evaporated by the star, and eventually it coats the inside of the glass. So eventually it disappears behind this kind of mirror shades effect, which we have to clean out periodically. Yeah, well, there you go. So we can try putting some gases in it maybe and see if we can get it to change colour. I don't know if does anyone have a question or anything at the minute at this stage?
Where's the card?
A 13 amp plug.
No. There's a slightly more complete answer.
What is it used for?
Interesting question. Well, originally it was intended as a way of making energy. And it can achieve nuclear fusion, and these are used, the technology is actually used in neutron sources, compact neutron sources for things like oil well exploration. So there are miniature versions of these that place down oil wells, and then the neutrons let off, allowing you to analyze the rocks around it.
Like a super X-ray machine.
Yeah, but what you can use for?
Oh, what do we use
It's an
it for?
artwork. It's got no practical use whatsoever.
Yeah, it's... I mean, we've got different backgrounds, I guess. Paul's background is as an artist. Mine's as a scientist. I've, I guess, for a long time been frustrated by how so much of science is just reduced to technology that nobody looks at. So, you know, most people have a cathode ray TV set in their house.
Or did have.
Or
Till
did have,
recently,
yeah, okay. Which is a relativistic particle accelerator. And the physics that's going on in your TV set is just amazing. Yet it's reduced to technology that nobody can really appreciate. You know, you turn on the TV set, watch the program, don't think about the fact that you've got a relativistic particle accelerator, turn it off, and that's that. And one of the
because
things,
Corrie's on, probably.
well, I know, okay, so it's worth turning off. But one of the things that I think we both wanted to do, and I particularly wanted to do with some of the stuff like this, is just give people an easier access and attraction into some of the science that's going on. You know, the number of people who've come up to this and just sit there and look into it. And they get drawn in. There's something about the rate.
It's very hypnotic. If you spend some time with it, you tend to lose time. It's quite strange. If you sit in a room with it, it hypnotises you. We had a guy recently wanted to put somebody on an EEG when they were looking at him because he thought it might have a therapeutic use. So maybe that's a possible use for it, but I'm not mad on finding a use for it personally.
No.
Can we, do you want to press the button, Colin? I'll try and put some, this is neon we're going to try and introduce into it.
So what we're going to do is we're going to, as Paul says, we're going to let some gas in. Is gas coming out?
Yeah, there we go.
So this is running on air at the moment.
We did have some helium, but Colin used it for his Valentine's balloon, our lab-grade helium.
So, oops.
So the pressure's dropped now, so the system's switched off.
So what we're really hoping is in a minute or two, so the pump's coming back on.
Then we're going to change what's in there for this, hopefully. This is really experimenting now, you see. This is what we're doing. Anything could happen. Nothing probably will. Oh, there we go.
Now,
there we go.
What you see on the screen is
Unchanged.
Pretty much exactly the same.
Yeah, but look at that. That ain't the same, though, is it? Will you verify this, please, people of the audience, that it has actually changed colour for the record up there?
And it's one of the interesting things. It actually, the photography that you see, it lets out quite a lot of UV radiation, like most superhot gases. And that tends to react with the camera sensors. So most gases that we put in this, the cameras record as a purple colour. What you actually see is something rather different. So this is neon. We think in a slightly more interesting way than your average neon sign. What are you doing, Paul?
Just put a bit more neon in.
Okay. we've got this odd relationship where...
What are you doing?
What we normally succeed... Well, I think we nicely demonstrate how science and art can work together. What we normally end up in doing is one of us says, oh, that sounds a bit dangerous, we can't do that. And then the other one says, yeah, go on.
If we put some goggles on and do it outside, we can probably do it. That's what we usually think. Actually, the thing we were going to do wasn't that dangerous, but then that's another story. But what happens when you put neon in here as well is quite interesting, because neon has very massive nucleus, so the inner grid evaporates a lot quicker with neon. And this thing, if we ran it on neon for a few days, as we demonstrated at a show in Berlin, the whole thing goes black in no time at all, because the inner grid just basically disappears. Should we try a bit of balloon gas?
Yes. So we'll try some balloon gas.
Which is basically helium and air. But this may not be that spectacular, but we'll try it.
Go on, I'll hold it. You press the button.
Okay. Goodie. Let's press the button. That's gassing all right, isn't it?
At some point we're going to find our voices go a bit squeaky as we're wasting all of this helium.
That was the other... We did have another experiment in mind at one point, which was to see how long we could talk in squeaky voices before we passed out. That might do it, yeah. Try that.
When we were practicing this earlier, it'll wear off in a moment. One of the downsides of doing this actually is we sat around this, playing with this, obviously laughing at the squeaky voices.
Go on then, a bit more.
And then one of us passed out. Because your reaction, the thing that makes you feel that you're suffocating isn't lack of oxygen, it's carbon dioxide. So if you keep breathing in a helium-rich atmosphere, you get rid of the carbon dioxide from your body. You just don't take any oxygen in. So slowly the world goes grey and then you fall over. We're hoping that's not going to happen here.
Try that.
Okay. Do you want some helium, Paul?
No, go on, let's have a go then. I can't resist.
Thank you, Colin.
So,
there we go, look, white, there we go.
Yes, once again, what we have on the screen looks pretty much identical to what we had before.
Yeah.
Thank you.
Thank you, Colin.
Thank you.
Another successful experiment.
Another success. What we actually have here looks slightly whiter. If we were to do this from scratch, we would bring the pressure right down to a very low value and put helium in, and it would actually look white, even if it does look a little bit red now.
Bit pinky, innit? It's got a nice yellow bit around the inner grid. I think it's running a bit hot, actually, Colin. Colin?
No, it's okay.
It's running a bit hot.
No, it's
I
okay.
think we should run.
Don't worry. No.
Okay, well, that's, there we go then, a star in a jar. I think that's about...
Thank you.
We can't move it, right?
Oh, we can switch it off now, yeah.